Good evening to everyone, and thank you for coming. Now, those who did not attend my first lecture in chess and math and wants the slides, they are on the website, and if you don't find them, you can email me, and I will give you the mail at the very end. And this lecture is about chess and machines and chess and computers. I would say in advance that I'm not an expert at all in this area, and AI and machine learning and so on, and indeed I made this research and this presentation to get to know it a bit better, at least on the conceptual level. And this is the goal of this talk, to show you the main conceptual differences between classical chess engines that were developed till almost 2015, till the great rust in machine learning, in AI, Google, DeepMind, and so on, and was the difference between this and the new type of engine, which are based on machine learning, neural networks, and so on. So the lecture would have three parts. Firstly, we would delve into the history of chess computers and how people dreamed about building chess machines, and then how it developed in the 20th century alongside with regular software. And then we would see some small but important theorem in game theory. Then we would see the main conceptual differences between classical engines and machine learning based ones. And the last part would be fun, because we would see three positions where even modern engines, I mean Stockfish 16 and 17 and so on, do not see the win for a very long time. One from a real game, and two from known studies. And also one of the studies would include a story of about Michael Tal, and I would add additional story, which is always fun to hear stories about Tal. All right, so of course, many years before the invention of computers or electronic computing machines, which happened in the 20th century, people wanted or dreamed about building a machine that can think in a way that resembled a man, or at least in certain tasks. Yes. And in the early 17th century, so about 1620, the famous French mathematician and philosopher Pascal built a mechanical calculating machine, which is called Pascaline. You can see it on the bottom of the slide. It's now in a museum in Paris. And the machine could perform arithmetic calculations, so addition, subtraction, like calculator, but a very, very simple one. Yeah. And you can see some gears and so on, so it did perform some basic calculations for the time. But of course, arithmetic is a very limited field of knowledge, and it wasn't such a great achievement even in that time. Yes, but still it's an important fact. And as you know, chess from its basically invention about 1700 years ago was considered as a field that requires very high intelligence, and even 200 years ago scientists were dreaming, of course, about building a machine that could play chess by itself. And the first such machine, which, as you probably know, is not a real machine, is something that probably some of you or all of you saw, is the Turk machine. So it's a nice story. So in 1769, Hungarian engineer, which was a part of the Austro-Hungarian Empire at that time, Wolfgang von Kempelen decided to build a chess machine to impress the Austrian empress at that time, Maria Theresa. Of course, we are in 1760s, so no computers, no electronic devices, and so on. And the machine was called the Turk. And why? So it was some kind of a dresser or a commode, so some kind of a table with some drawers, and a chessboard on it. And behind the table there is a model of a man dressed in a Turkish robe. We will see it in a second. and the man's hand made the moves on the board, on the real physical board, and it gave the impression that the machine was playing by itself. Now, of course, it's not true, because we are in 1769, and a strong and short Austrian master, which was cleverly found by this engineer, was cleverly hidden inside a drawer, so that when you open the drawers, you see an empty space with some gears or something like this. And this was done by a clever system of mirrors that projected one another and hid this chess master, which was strong enough to beat many players. Maybe not the top masters like Philidor and so on, but many players. And many good players lost to the Turk, and the two most notable are Napoleon himself. As you know, he was a very good amateur. There are some games even in the database. He lost, he was very angry and very furious after this loss. And also Benjamin Franklin, the American polymath, one of the founding fathers of the United States. He was also quite a good, strong amateur. They both lost. The secret of the Turk was only discovered decades later, and people, of course, couldn't understand how it's possible, because he showed the interior of this cupboard, of this dresser, and it was an empty space. Yeah, the machine was put in some museum in Austria, or in an Austrian Empire, and unfortunately, in 1854, during a fire in a museum, it was totally destroyed, and two replicas were created in the 20th century. One is in a museum in Germany. I don't remember exactly. I think in Köln or something near Köln, and the other one is, I wrote here, is in Los Angeles. We will see now one of the replicas. So on the left is an illustration of how the real machine looked like. And on the right is one of the replicas, which is in LA, in Los Angeles. Yes, so you can see how the master was cleverly hidden and so on. But this is, of course, some anecdote and a joke. It's not the real start of chess machines. And now we dive to the 20th century, where it all started in terms of electronic commutation machines. So in 1940s, the field of computer science and actually building real computers, and not only theoretical ones, started, and the founding fathers are whose founding fathers are the great British scientist Alan Turing. You heard of him probably, and maybe some of you saw the Imitation Game. He was also a cryptanalysis. He was in a secret group in Bletchley Park during World War II, trying to decrypt the German Enigma machine, and also he invented many revolutionary ideas. The other one is John von Neumann. I will tell a few words about him, because in my view he's one of the smartest people that ever lived. And the other one is the founding father of information theory, Claude Shannon, also a known figure, who calculated or estimated the number of legal positions in chess. Turing was known by inventing the Turing machine, which is a basic model of a modern computer, and also he proposed the famous Turing test. And the idea in Turing test is to try to find out if a machine is intelligent. And so he proposed that a person would sit in an isolated room, and in two other rooms you would have a machine and a human, and he would communicate both with the machine and with the human, not knowing who is in which room. And if in a significant amount of cases where Turing I think said it should be at least 30%, the man could not identify where the human, where the machine is, it means that the machine passed the test and it's intelligent enough. Yes. Of course, today it's very easy with AI and so on. You would never guess it, but then it was a good test. In the late 1930s, the first electronic computer was built. Of course, it was not, they were not the computers of our time with chips and so on, but very basic electronic parts like in TV and so on. And in 1946, the first chess program was written for the American computer ENIAC. It was on a 6x6 board and not by 8x8 board, without bishops, because the hardware of this time was so primitive that it could not cope with the huge number of variation of chess, so they had to truncate the board, and for symmetry purposes they took the two bishops so that you won't have imbalance, yeah. It could calculate to a depth of like 4 or 6 half moves, so like 2 or 3 moves. So these are the founding fathers. Now a few words about John von Neumann in the middle. He was a Renaissance man in the middle of the 20th century. Now, just to name a few of the areas of his research, he was a nuclear physicist, and he was a prominent figure in the notoriously known Manhattan Project, together with Oppenheimer. Some of you have seen the movie. He was one of the founding fathers of quantum mechanics in physics. He introduced game theory, which is today one of the most important branches of mathematics and economy, and the Nobel Prize in Economy, which is held, the ceremony held here, many times the winners are mathematicians that work in game theory. He was also pioneering computer scientist. He invented sorting algorithms and some other concepts, and he also helped in mapping the DNA. So just a few of his achievements in the 20th century, not in 16th century. Now, according to Claude Shannon, which is the founding father of information theory, there are about 10 to the power of 120 legal positions in chess, not only up to move 40, which is usually calculated, but in general, which is much more the number of atoms in the visible universe, which is 10 to the power of 80, roughly. It's much more than this because it grows exponentially. And only in 1950, Turing wrote the first complete chess program for a computer. Of course, it was very weak. So in parallel with the development of chess software, when at that time it was dedicated to chess and not, of course, part of a general computer, it also developed in the Soviet Union. And actually, one of the pioneers in this field was the 6th world champion, Mikhail Khotvinik, who had also a PhD in electrical engineering. In fact, from 1948, when he won the title in a 5-player famous tournament, till 1951, his match with Bronstein, which he barely drew 12-12, he didn't play chess at all and work on his PhD thesis, which is unthinkable today, to leave chess for 3 years. Yeah, I mean, modern top grandmaster. In the mid-60s, an M20 chess computer was developed in the Soviet Union, and it lost to David Bronstein, but according to some expert, it played on, like, say, 2200 level already, which is decent. Then in 1968, there was an anecdote, relatively famous British-Scottish international master David Levy proposed a bet that no chess program would beat him in the next 10 years, so till 1978, and he won the bet. The last match he won 4-2 in 1978. In the 1970s, another Soviet program was developed called Kaisa. It was much stronger already. Also, of course, you have to understand that the hardware, yes, the parts was much better. Intel was already developing some chips, and so of course the program got stronger and stronger just due to calculation abilities, even without improving algorithms. And then in late 1970s, the renowned American computer scientist Ken Thompson, which was co-founder of the famous C programming language, created a machine which was called Bell. He worked in Bell Labs, in the telephone company. You can see it on the right. It's not of the size of the full room, but let's say 1 meter on half or something like this. It could already calculate hundreds of thousands positions per second, and it won many computer tournaments in the early 80s. So it was quite a strong machine. And in 1980s, the IBM company created their first program, Deep Thought. So they loved the word deep. So all the later chess software was called Deep something. And in 1989, this Deep Thought played a short 2-game match against Kasparov, who was of course 4 years already world champion. He beat it to 0, but the games were interesting, and the machine already, this software already played on the level of a good grandmaster, like 2600, something like this, by today's standards. And then something you probably heard of. Then IBM decided to invest a lot of money, and they upgraded Deep Thought. The next version was called Deep Blue. So it was a computer that was designed solely for playing chess, and in spite of modern times, it took an entire room. Yes, it could calculate 200 million positions per second, and it challenged Kasparov to a match with the title of human race, etc. And some people know the match that he lost in 1997, but in fact in 1996 there was the first match in Philadelphia. Kasparov won the match 4-2, but he lost the first game, and it was the very first time Chess Engine beat the reigning world champion in a classical game. They already lost in Blitz and Rapids and some Intel tournaments, Grand Prix tournaments that were in the 90s. But he won the match, and they suggested a rematch in 1997, and he accepted, of course. And there are several movies about this match, including the recent one. And of course, there was a scandal that I will tell in a moment. In 1997, he lost 2.5, 3.5. It was a tie before the last game. In the last game, he played a terrible variation of the Caro-Kann and lost the game. And during the time, he thought that some grandmasters in the team of Deep Blue helped the computer in positional decisions during game 2, when the machine missed perpetual check, which Kasparov didn't do, and not an easy one, by the way, but should be an easy for a machine. But after time, Kasparov said that he doesn't have such opinion anymore, and he thinks that everything was fine. Of course, they have a lot of consultants. Joel Benjamin, Miguel Illescas. He was also one of the He worked with Kramnik later. Yeah.
But this Caro-Kann game you mentioned, this position initial was from the opening book.
Yeah. So.
They changed the opening book.
Yeah. So there's a story.
So use Fritz 5.
Yeah.
Opening book.
Yeah.
Just to irritate Kasparov.
Yeah. So in fact, Kasparov played very rarely the Caro-Kann, and he wanted to surprise the computer, and he thought that the computer would not sacrifice the knight on e6 in this Karpov variation with 97, but he did. And the story goes that Joel Benjamin inserted this opening idea into the book of the computer a day before, a couple of days before, something like this. And after this, the position of black is bad. Not losing, but bad. And he just collapsed psychologically, but still the match was even, yes? And because it's a corporation, they, of course, didn't want any more matches because their stock rise and so on, and they dismantled the machine. Now it's in a museum in Philadelphia. Later, and then we already in the era of rapid advancements in various software, two Israeli programmers came up with the Deep Junior software. It had a deeper understanding, and Kasparov faced it in 2003, a 6-game match, which ended in a 3-3 tie, one win each. It's some some good sacrifice of a bishop on h2, if I remember correctly. And throughout the 90s, since the establishment of the chess-based company in Germany from the mid-80s, the main chess engine of chess-based was Fritz, and they started to develop various versions of Fritz, which was the only choice for GMs in the 90s, Fritz 1, Fritz 2, and so on. And there were various versions of Fritz. So Kasparov in 2003 also played against the 3D version of Fritz. Some of you saw these images, him wearing glasses, yes, and so on. So he saw the pieces in 3D. He tied the match 2-2. In 2002, in the United Arab Emirates, Kramnik played a match, an 8-game match with Fritz 8, and he drew 4-4. And he told it was enormously hot, like 40 degrees, and he couldn't get out of his hotel and so on. And in 2006, just after he won his scandalous match against Topalov that united the chess world, he played against Fritz 10 and lost the match 2-4 with his famous oversight of mate in 1, when the knight was on f8 and the queen mated him on h7. And actually he needed win on demand in the last game. He played the Najdorf, which he almost never played and lost, but the match was even, so it's not that, and we still had chances. But unfortunately, the same year, Michael Adams lost to a program called Hydra 5.5 to half, which was terrible because he was number 7 in the world at that time. And as I said, Fritz is the main chess, the default chess engine of chess-base from the mid-80s. And since around 2006-2007, we don't have almost any chance against any computer, even without material, even without a piece. And many programs came up since then. And today, as you know, the strongest are the freeware Stockfish and Commodore also. They play on a level of, let's say, 3500, which is unthinkable for us. What it is, it's like to think about an IQ of 500 and so on. And here you can see a picture of Kasparov in the second match with one of the programmers of Deep Blue, or Ray Campbell. So since 2006 and 7, we don't have any chance, so it's hopeless. And now about the theoretical part of chess. So chess is a game that has certain properties. The first one is a complete information game. So you see everything, yes, which is on the board. The players play in turns, yes, so it's not like soccer or something like some other sport. And there is no inherent element of luck. Okay, you can have luck when your opponent blunders the piece, but it's not luck which is a part of the rules of the game, yes. Other games with such properties are checkers and tic-tac-toe, which you can play not only on 3x3 board, but on an n-by-n board. Not all games are of such type. For example, if you take Backgammon, it's not of this type because there is an element of luck, because you throw dice, yes? It's still complete information. And of course, poker. In poker, you don't have a complete information because you don't see the cards. And of course, you have an element of luck because you shuffle the cards. So we are not going to talk about the second type games, but only of the chess types games. And regarding the games of the first type, so you play in turns, you have complete information, and you don't have luck. There is a famous theorem in the very beginning of game theory. So when game theory was very, very, very elementary, by the German mathematician Zermelo, who is also one of the founding fathers of set theory in mathematics, which says the following: that every game of this type must one of the following possibilities should hold. There is a winning strategy for the first player, no matter what the second does. There is a winning strategy for the second player, no matter what the first does, or each of them can force at least a draw. Now, you can think it's a totally trivial theorem because, of course, one of these options should hold, yeah. So in chess, what does it mean in chess? So in chess, for example, if there is a victory that guarantees a win for the first player, so for white, it means that there exists the first move of white, so that no matter what black would respond, so in every for every move of black, white would have a move that for every move of black and so on would bring him to the victory. Yes, so those who studied logic, it's kind of quantifies it. There exists a move such that for every move there exists a move and so on. And of course the same for black. So if black has winning strategy, that then we know that no matter what white starts the game with, you would have a response that would lead you to the victory, no matter what white does. Yeah. Now on the surface, again, the theorem is completely trivial, but on the other hand, it may be possible that in every strategy you can have branches that you cannot force at least a draw or a win. We will see now that your intuition that it cannot be the case, we should prove it, yes, and not just think about it intuitively. So the theorem is clear, yes, I mean, theorem is, and the proof is short and beautiful. So to see this, we would represent a chess game as a tree, which is usually done in such games. So what is a tree? Is a collection of circles, which we would call nodes, which represent a position, and edges, which represent moves. So here you see such tree. So the nodes are some positions, and the edges are some moves. Now, of course, in every level of the tree, there is someone's turn to move. So in this tree, white is in the first level, yes, black is in the second, and so on. And every edge is some move. I didn't write here bishop d7 or something like this, but and clearly you can represent any game as a branch of this tree, yes? It's clear, yes? And so, this which I said here, at the very bottom of the tree, we would have winning positions, which are checkmates, yes, and we would have drawn positions, which are stalemate and insufficient material. We won't consider other forms of draws like agreement and so on. For us, every game would play till the end, yeah. And we would call these nodes leaves, because from them we don't have any edges down, which of course remind us leaves in a tree. They are the last ones, yeah. And so every such leaf we would cover white if it's a win for white. So if white checkmated black, yes, you would cover the leaf with black if black won. So if black checkmated white, and we would cover the leaf with gray if it's a draw, yeah. And now we are going to cover bottom up all the other nodes. How we will do it? So, for example, here it's white to move, yes? And white has two moves. One leads to a black leaf, and the other one leads to a white leaf. Of course, white would take this move, yes, because he wants to win usually, yeah. So if you are white and you have one of your children covered white, you cover yourself by white, meaning that you have a winning move, yes. And why we are going bottom up? Because for leaves we know the answer, yes, and we must cover the tree from bottom up, from when we know the answer till when we don't know, yes. Now, if it's white to move, and here you see that both of the suns are gray and black, of course white doesn't want to lose, so it would choose the drawing move, and then you cover it by gray. So if you are in a certain level of a tree and you're white, you look on your children, yeah, which have some color, and if some of them is white, you cover yourself white, because then you can go to this node and win, yes, because from this node you can win, yes. And if you have no white suns, but you have someone which is gray, you cover yourself gray, yes, because then you can at least guarantee a draw. And what's the bad case? That all of your children are black, and then you cover yourself black because you lose, yes. For black, it's the same, but the opposite. If it's black turn, then if you have at least one child that is black, you cover yourself black because you can win. If all of them are white or gray and you have a gray one, you cover yourself gray because then you can avoid losing. And if all of your sons are white, you cover yourself white. And so you can see that you can feel cover this tree bottom up, yes, because you have more and more answers for the positions. And what is the winning strategy? This tree has a root, so it's the very top node, which is the starting move of white. If the root node is covered white, then white has a winning strategy, yeah, because it means that from the top node they can have a white path from the root to the leaf, and you can see this path, yes, on the right, because it means that I can force black to go to a node which wins for white, yes. If the root was covered black, then it means that black has a winning strategy, and as we believe about chess, you don't have either, so the root would probably cover gray, yeah. The tree covering is clear, yeah. Any questions about this? Clear, yes. And so we know, of course, that there is one strategy, but of course we can never calculate it because it would take us centuries with the best technology, and also we cannot keep all the data. It's too big. And now, finally, let us discuss how classical engines work. So this is all engines still AlphaZero or Google-based machine learning neural network engine. So from Deep Thought to Deep Blue to Ripka, Hydra, Shredder, Fritz, etc. Yeah. So till now, all of the engines worked in the following manner. So now each position in chess for this engine gets a numerical evaluation. How it's done? It's done according to some large amount of rules of thumb that were introduced into the software by the programmer, so by us. So we tell the software what is good and what is bad in chess, or at least in most of the cases. Yes. Of course, according to our knowledge of the game. Yeah. And such rules of thumb are called heuristics. Of course, you heard the word eureka when some scientist has some revelation. So in Greek, it's to find or to discover, yes? And these rules are good in most of the cases, but of course not in all of them. And there are simple examples of such rules, like it's good to place a rook on an open file. Yes, it's good not to put all the pawns in the endgame on the cover of your bishop. It's not good to put the king in the opening on e5. And so on, yeah. So we hardwire it in the computer. So we give him the knowledge. It doesn't discover, yeah. And of course, there are much more complex rules. And as chess computer programming developed, it got more and more complicated. All right. And then a score of 0 for a position means that the position is equal, as you know. Positive score means an advantage for white, so from 0 to half is slight advantage, from half to 1.5 approximately is big advantage, and then it's winning, and so on. And in a symmetric fashion, a negative score is an advantage for black. Now, this symmetry would in fact help us. It's not like the Celsius temperature that we can have other metrics like Calvin, which have no negative numbers. In fact, here the symmetry of negative and positive numbers would help us in this chess engine. So this you know, all of you of course, because you use engines. And then the engine calculates several moves ahead, let's say 5 moves or half moves, yes, ahead, and gives an evaluation for each position on the way, yeah? And then it chooses the position whose evaluation is the best, yes, and gives you the first 4 lines, and so on. And of course, as we previously represented the chess game with a tree, here we would also represent it with a tree, but with a different tree, which is called minimax, also an idea of John von Neumann. You will see why it's called minimax in a second. So there, of course, again, every node, every circle would represent some position. and every level would say who's torn in it. And now we would understand why it's minimax. Now, so let's say we reach a calculation at depth 5. So let's say 5 moves or half moves as you want. So we are on depth 5, and we give there for all the positions at level 5, we give them an evaluation according to all these heuristics. Yes, so one position gets 1.2, the other one 0.6, and so on. So in level 5 we have all the positions. And now we don't evaluate the positions on levels 4, 3 and 2 just by these rules, but we do the following. So now let us assume that we are in level 4, so one above when we have the values already, and let's assume it's white's move. Yeah. And so what are you going to do? So the move of white would lead us to level 5. Yeah. And for each white's move, we see the evaluation of this position level 5, and what we would choose, the maximum one, because we want to maximize white achievement. And so we would put the evaluation of the node in level 4 with the maximum value of his children, yes, of the position we can reach from it by this move, yeah. And so because we want to maximize. Now for black is similar, but what we want to do for black, we want to minimize the evaluation, because negative scores are the ones that are good for black, yeah. And if in all of the moves it's white's advantage, you want also to minimize it. Yes, it would rather go to a position which is +1 and not +5. So for black, we want to choose the move that leads to the minimal evaluation, yes, and for white, for the maximum. And now you understand this name, Minimax 3. And it's clear, yes, the idea is clear. And so we can fill up the tree in this fashion. And here where the symmetry helps us, yes, that it's negative and positive, yes, because we use the notion of maximality and minimality. And here is an example. So here it's a tree of depth 3 half moves, and let's assume that the last level is black storms, and here we calculated all the evaluations using the rules that we have. So no minimax, just for every position we applied all the rules, and we got that here the evaluation is -1, here it's 3, and so on. Now here it's white to move, yes? What's the maximum value between these two moves? It's 3, yeah? So of course we would put here 3, because we know that we can choose a move that would lead us to 3, yeah? And here you see that it's max, yes? Because here we maximize, because it's white. Here we have 5 and 2. We'll put here 5. Here we have huge advantage for black, yes, but white wants to reduce, yes, the advantage of black, and so we will put here -4, because we don't want to get to -6, yes. And so now here it's black's to move, and so I put here min, as you see, yeah. Here black's to move, so black wants to minimize the advantage of white or increase his. So here it has 3 and 5, so of course it will choose the move which gives white an advantage of 3 and not 5, yeah. Here -4 and -1, of course black would choose a move that gives him -4, yeah. And this is why this tree is called minimax. So you alternate. For black you calculate the minimum of the evaluations of the children, and for white you calculate the maximum. Yes, so it's clear. So this is an idea of John von Neumann, and here, and this you can do for any depth. The tree would get bigger and bigger, you would have more and more time. The idea is clear, yes. And a theme that was introduced now, because we have a lot of variations in chess, and we cannot calculate all the positions till depth 20. Yes, we just don't have nor the time nor the resources. Clearly, it's better to throw out some stupid positions where the evaluation really drops. Yes, like you hang a queen or something like this. Yeah, which is called alpha beta pruning. I don't remember what's the origin of alpha beta, but doesn't matter. The idea is that first moves that significantly reduce the evaluation we don't drop them entirely, we put them on hold, yes, and at first we only evaluate branches when we don't drop drastically, yes, let's say from 1 to -5 or something like this, yes. This can cause a failure of the computer recognizing some deep sacrifice that you cannot see its effect, let's say, in 2 or 3 moves. And this would be exactly the examples that I would show you at the very end. You have a link for them here, but I would show it for your event. So all of the examples where modern engine fail is those that he doesn't understand either some deep sacrifice or that some big material advantage is not actually a win. Yeah. So in old times when you can have wrong bishops and 6 H pawns and he still didn't understand it's a draw. Now it does. Yes, but still. And you would see examples at the very end. And so the last part is the machine learning based chess engine. So what is machine learning? So it's an area that began in computer science, in theoretical computer science, which is of course closely related to mathematics, in the beginning of the 2000s. So machine learning, or ML as it said, that the machine should learn by itself what's good and what's not good. But of course it cannot be entirely by itself. We have some methods and algorithms that says to it how to quantify the data it collected, how to categorize it, but essentially it does simulations and it understands what's bad. So we don't tell her that you should put rooks on open files. Yes, it should come due to simulations and seeing what positions he or she simulated a lot of games and lost, and so on. And so in this framework, the machine makes a lot of simulations of some game or system, yeah, and it tries to understand what's the best way of action or play in most cases, and what is less good. Now, of course, as I said, the machine doesn't do it by itself. There are machine learning algorithms which tells it how to categorize the data and how to quantify it and in what areas to look. But we say to it the how and not what. Yes, in contrast with the classical engines. So in chess, for example, as you saw in many games and books, when AlphaZero emerged, many simulations have shown that when you push the flank pawn, the H pawn, let's say H4, H5, and 6, it's good in many openings that we didn't consider it good in the 90s when we analyzed the openings by ourselves, even if there is no direct attack, like there is no pawn on G6, like in the Dragon, let's say, yes, and you try to open the H file. And why it got to this conclusion? Because it simulated a lot of game and it saw that it should be good in most of the cases. Yeah. So in recent years, Google or DeepMind, the DeepMind corporation Google has invested heavily in machine learning algorithms for chess and Go, and they created 2 software, AlphaZero and AlphaGo. And AlphaZero conducted a series of matches against Stockfish, and they more or less roughly equal now. You heard one of the main figures in DeepMind, Denis Hassabis, who won the Nobel Prize in chemistry. He went there after it. He was a strong chess master. Was a UK champion under 14, and he was one of the founders of this AlphaGo and AlphaZero project. They also managed to beat the best humans in Go, which was much more complicated because this game has a lot more variations and it has much deeper strategy. But also there they establish superiority, and so. The main difference between the machine learning engines is and the classical game is that here we do a lot of simulations of full games. So our tree is depth first search. So we simulate till the end and write the result. Yes, and then make some kind of a statistic. Yeah, that from this position we won as white, let's say 69% of the games or something like this. Yeah, and in regular engines we analyze not so deep, not the entire game, and we check many moves. And the computer analyzes the positions according to the rules V hardwired in it. Yeah, and here again there are algorithms that help the machine to categorize what runs. And so AlphaZero started really from scratch. It knew the rules of the game, and then he started to come up with the best openings that it took top grandmasters years to discover. Swidler talked about it, that it came up in a couple of hours to the best, to my best analysis in Grunfeld defense from the 90s. Yes, and such search can be represented by another form of tree, which is called Monte Carlo tree. Why Monte Carlo? It's a famous gambling city, so this is the name. This is the name. And so the engine tries to learn certain structures, pawn structure or motifs that appeared in the good simulations where it won. Yeah, and as well as characterizations of certain positions that led to a loss. So, for example, it would immediately understand that it's not good to go in the opening king e2, king e3, king e4, and so on. Yeah, because it would lose all the games. So it won't do it. Yeah, but why it won't do it? Because the machine learning algorithm would help her to categorize this data. And then it's also important that we don't want to simulate all the positions. So at a certain point we already have a characterization of bad positions, and so it would drop them or give them less probability. So we can simulate not all the positions with the same probability. We can give, let's say, 90% to this one and 10% to this one and so on. And then we can, of course, reduce the number of calculations and simulate more positions, which is better statistically. Yes, if you simulated only 10 moves, 10 branches for a certain position, it's not good. Yes, you have to simulate thousands and thousands, yes, to get some good statistical data. And here it's a Monte Carlo tree. So again, each level is whose turn to move it. And the top level is white to move. And you can see it's simulated 21 full games, so till mate or till draw. And we always write in how many white won or how many points white scored. So here you see 12 from 21. And on the second level, you see how it spread. Yes, so there was 10 games in this branch, 8 in this, and 3 in this. And on the right branch, in fact, white lost all 3 games. Now, of course, 3 is a very small number, but it would be, if it would be, let's say, 0 from 20, probably it's a bad move. Yeah, and these are simulations of the entire games till the very end, and then you write 0, 1, or half. Yeah, and then you can statistically know what branch is good, and then try to see what the characteristics of this position. Now some basic advice when analyzing with engines. Many of them you already saw or heard. So most classical engines like space advantage, and for example in openings where white enjoys space advantage, like the King's Indian, for example, I mean the regular variation, not the exchange and so on, it's too optimistic and it gives like plus 1.2 in some lines, and it's not the case in many such lines. Yes, so it likes space a lot. Yes, classical engine, so you should be skeptical in theoretical positions. The second one, in endgames, especially with pawns, when you can win only by promoting a pawn, yes, and not by some crazy maybe blunder, yeah. If there is a significant advantage to one side, let's say plus 2 or plus 1.7, but it's shown in many lines, it means that the computer doesn't see how to promote a pawn, and usually it means the position is a draw, not an easy one. But if you have the same evaluation and a big one, but not a winning one in many lines, it means that it knows you have an advantage, but it cannot see pawn promotion. Yes, and it's probably a draw if you analyze some endgames. Now, following the explanation of pruning, if you analyze some deep sacrifice, make some more moves or wait and give the machine time to see if it's good or bad, and not just see what's the evaluation after 20 seconds. Yes, because it may not understand why certain sacrifice is good. When you analyze some opening ideas, in some lines the engine may show equality, but the moves that lead to equality are much harder for humans to find. Yeah, than in some other line where the computer gives 0.4. Yeah, but it's very easy, let's say, for black to get to this position. Yeah, so always think from the sense of the human. Where so if it's a draw but you have only one move at every point, of course it's the favorable line, and not a line where you have even 0.6. Yes, and it's easy to draw. And in very close structures, it's the only sort of positions in chess where you can have some chance to beat the machine and draw the machine, at least when you have several grandmasters work together, top players. Yes, and in very close positions, when you have only maneuvering and no tactics, it may give you not the best evaluation. And the last advice, which, for example, both Boris Gelfand and Swidler repeat many times, when you analyze opening or some other position with an engine, you should always try your best to understand why certain move is bad or good or bad. I mean, not tactic when you blunder some material, but some positional moves, or why this move order is worse. You must understand why, because otherwise you won't understand the structure and the ideas. Now glance to the future. So as you know, today it's very difficult to get an advantage even with white in classical games, and you know the interview with Dubov that he said that against Pragananda in the World Cup he didn't prepare at all 10 minutes with the phone because he couldn't find any ideas, and people already play some extreme sidelines like Aronian and so on because they don't know what to do. Yes, but still the level of computers is extremely high, and all top GM do not have holes in their analysis. Therefore, it's likely that we will have more Chess 960 tournaments, not only the elite ones, but also some opens and so on, or maybe some other variants of chess, like chess without castling, or some other stuff which ruin or divert a bit the openings. Of course, you will have more rapid and big tournaments, which we have nowadays already, compared to the 1990s. And in the battle between the classical engines and the machine learning engines, probably the later expected to become stronger, because the machine learning field is still relatively new. It's just 20 years old, and so we have a lot of room for improving the algorithms. And in terms of pure artificial intelligence, AI, like Chat GPT, etc., at this point, pure AI algorithms are still weak, and you see that if you play chess with Chess GPT, it's still weak. Previously, it even made illegal moves. Now it does already, but it's still quite weak, because it's not. Its purpose is not to play chess. Yes, it cannot collect information on internet to play good moves. We need specified software. So this is the last part. Now we would see the free example when the computers doesn't see the win. But any questions till now? No questions. So as you know, during the dark COVID times, there were a lot of online tournaments from top to bottom on chess.com, Lichess, etc., and local federations did a lot of tournaments. And one of them was in 2020 itself, so in real dark COVID times. And in one such tournament, there was a game between Anand and Nepo. So it's May 2020, so the real beginning of the pandemic, online Nations Cup. The game lasted, as you can see, 17 moves. Now it's very rare that a player of Nepos caliber loses in 17 moves, even to Anand. Yeah. And in an interview after the game, some journalist said to Anand that you know that the computer doesn't see even why it's good, why it's bad. Now here I put Stockfish 15, which is of course extremely strong. Yes, because in 17 it recognizes for a blink it doesn't see the correct move, but then it immediately recognizes it. But I wanted to show, I wanted you would see that it doesn't recognize it. Yeah, and Stockfish 15 doesn't see it for a long time. Yeah, so let's see the opening move. So Eduard, if you want to add some comments on Grunfeld, because I'm not an expert. So it's Bishop D2 Grunfeld. Also possible line, not on e4, takes, so of course Vishy knows the theory, Queen d2, f4, and we reach this position. Of course the pawn is pinned, yeah, and here Bishop e6 looks a natural move. Yes, you want to protect the pawn, to put the bishop on a stable square, yes, and it looks, in fact, when Jan played Bishop e6, it was the start of his problem. And then, as you can see in the notation here, the next moves of the games were Bishop e6, castles, and d4. The move, this sequence, loses by force. For black, we will see in a moment why. But I just turn on the engine, and please look on the first line. It would show you, or it should show you, Bishop e6, castles, d4. Okay, I turn on the engine. Yes, you see Bishop d6, castle, or it was there previously. Okay, just a second. I would do it again because maybe he remembered my analysis from the past. Yeah. You saw it, yes, previously, yeah, here, yeah, Bishop e6, okay, after some times he sees, now modern engines, but you saw that he showed this, yes, for a couple of seconds, maybe we'll do it again, because he has some cache from previous data. In the two next examples, it would Bishop e6, castle d4. You saw it. Yes, it was on the screen. Now it loses by force, and now see how the evaluation changes because he already realized it. Castles, and Jan played d4, which looks promising. He has a strong center, yes, and so on. What was the move of Vishy? Now here you can see the computer already. The move was f5, sacrificing the bishop with the tempo. Yeah, and due to this, the engine initially dropped this line because he sees bishop sacrifice, but he didn't see the end of the attack. And you can see that there would be now a mating attack on the dark squares. Bishop c4, Jan took. Now if you don't do it, if you take here, Queen h5, and it's almost impossible to stop the mate because there is no f6. F pawn is pinned. Yeah, and it's amazing you cannot stop mate, but on the other hand you have two non-developed pieces. Yeah, so bishop takes c4, e5, and now you cannot stop the idea of Queen h6 and knight j5. Queen d7 he tried, f6. Another idea, and now you cannot stop Queen h6. Queen h7 mate. Here he resigned. So no other move. So the engine saw that not only you lose the bishop, but it comes with the tempo on the rook. Yeah, and he dropped this position immediately, and only after a while, yes, it returns to it. Yeah, and sees that this line is bad, and it dropped it. Yes. Here you saw this line for a second. Still the second line. Now the third line. So as you give it more and more time. The second one is a beautiful, beautiful study of Mario Matosh, a Czech composer. We would not solve it because it's extremely difficult. Somebody saw it or not? You saw the study, yeah. So you know that it's extremely difficult to solve, yeah. It's white to play and win. Now I turn the engine. Here he would not recognize it for ages. Okay, you see, draw in first two lines, and you can keep it for many moves. Yes, and it would still show a draw. And now I would intentionally keep the engine working because you would see when it gets that it's not a draw. And why? Because the win involves deep sacrifice. Queen c8. Of course, the idea is bishop e7 with mate. Yes, the queen is pinned. Yeah. Okay. King g8 is almost the only move. Yes, because otherwise, so queen e6. I just take and g takes h7. What else? Knight c7 loses to bishop e7 check. The queen is pinned. Yes, he cannot take the bishop. And g takes f7 or g takes h7. Both I think win. Yeah. So king g8. Just not get aware of the threat of bishop e7 check. Still 0.00. Yeah. And now see this move. Bishop c7, totally suicidal, and instantly he gets, so when you insert the sacrifice, he understands that it wins, and you can see the mate. Okay, something like this happened with the famous move bishop h3 of Shirov against Topolov in Linares, knight 98. The computer, before the move, didn't realize it wins, but when you put it by force, it immediately sees that the king
Maybe
comes.
two more.
Yeah. But let's see the end of the study. So you see the engine immediately, and everything was forced. So what's the idea here? Okay, he must take the queen because no moves. Yeah, the only move is here. Then you take here, yes, or even on queen f8. G takes h7 and you lose the queen at least or get mated, I don't know. So queen c8 is forced. Now how can you win queen down? Yeah. So you take and king h8 because king f8 is mate. Yes. And now this is the whole key of the study. Bishop and here you threaten not discovered check but discovered mate. And so the only way to stop it is that the queen would both give the check and eat and take the bishop. But there is another threat which is f8 queen, and now you can see that you cannot stop all of the threats. So queen c5 stopping f8 queen. Now it's not mate because if you move with the king, I take the bishop. Yes, because I attack the bishop. Yeah. Now what to do? Bishop b2. Threatening again, king e6 mate, and the queen must control the f8 square and also take the squares from the king. Knight c7 takes the e6 square. Yes, so the king cannot go to the fifth rank and he cannot go to e6 and e7, so no mate for now, and f8 is also protected. Now a very beautiful move, bishop f1, so you see the dance of the bishop. And strangely, you don't have moves. You're in Suk-Swang because if you move the queen, the king would be able to go to one of the squares. If you move the knight, same, yes? And you have two threats, f8 and the discovery. And so the only moves that you have are pawn moves. And so a4, bishop b2, so the dance of the bishop. a3, bishop a1, a2, bishop b2, a1 queen, take. And now you must get mated. Knight d5, king here, check. Knight c3 is the only move, check, you take, and f8 queen. It's almost not human study to see this idea, but beautiful idea. I think that the computer doesn't see it. Yeah. And the last study, which involves also the story of Michael Tal, also famous study by the Dutch composer Gijs van Breukelen, who never published it, but according to him, he developed the initial version in 1970. So that's why I wrote, and I asked the famous composer, grandmaster in composition, Johann Afek. He also told me that he talked with him and he invented it in 1973 or 74. It was really published only in 1990. And it got very famous when in 1987 there is a famous Swift tournament in Brussels, top GM. Garry Kasparov won together with Ljubomir Ljubojevic, the legendary Yugoslavian grandmaster, and visited the tournament British then young grandmaster James Plaskett. You probably heard the name. And he was shown this study a couple of months before, and he went to the tournament and showed to some of his friends. And then he challenged the top grandmasters. So Tal played there, Korchnoi, Ljubojevic, Kasparov, Karpov, all the elite. And in the free day, they really struggled in the lobby of the hotel and couldn't solve it. And Tal was always also there. By the way, Tal didn't supposed to play in the tournament, but the late Robert Hubner got sick, and Tal, who was a journalist, he was also a journalist, yes, in the tournament he replaced him and finished with +1, by the way. Tal also couldn't solve it, and we know the calculation abilities of Mikhail Tal, and the story goes like this. It's a true story. He left the hotel and he went to walk in the park. He returned after half an hour. He solved all this puzzle in his head, so blindfold. He went back to the hotel, to Basket and to the GMs, and showed them all the solution from the beginning till the end, which of course was right. So this is one story of Tal, and the other one you would see after the study. So here, black is both a piece up, and he has two extremely dangerous pass pawns, e3 and c2. So it should be winning, or at least much better. Yes, I turn on the engine. You should see the evaluation. So we expect it to be in the minuses, and it is. The computer doesn't see straight win like -10, but it's winning. Yeah, you see in all the lines. Yeah. So why white cannot put the queen on d8? Because you have knight f7 check. You win the queen. Okay, you give one piece back, but still you have huge advantage. Yes. So what to do? It should be something forced. Yeah, and it's absolutely unreal to think that the idea is to mate the black king. Because it's so safe now on the 7. How the hell with two pieces you would mate the white king on an open board? So the first move is knight f6 check. So you cannot go to the 8th rank because then a queen will check. Yeah. So you have actually two options here. So first of all, let's see king g6, king g7. Yes. So what will be in king g7? It's knight h5 and the main line, which you'll see in a second. But what would be on king g6, which is another move that doesn't go to the back rank? Here we have bishop c2 check. Yeah. And you must take the knight, and then queen v check again. Yeah. If on bishop c2 I go king g7, knight h5, and then I'm forced to go to f7, and I take the forking square. You see, I queen, and you don't have a fork. So king g6 doesn't work. So we are going to see the main line, king g7, knight h5 check. Again, you cannot go to the back rank. If you go to h7, bishop c2, yeah, and the line that we saw, yes, now you must go to the back rank. I queen v check. Yeah, is it clear? Bishop c2. Now, so after after knight h5 check, you must go king g6. So everything is forced. See that black's advantage is huge here. Yeah. So it doesn't see it, just doesn't see. And this is the key idea. Bishop c2 check. So being a piece down, I sacrifice another piece, which is crazy in a white piece endgame. It's not that I have rooks and queens. Of course, you must take. Yes, you must take the knight. You cannot go to f7 again. I queen the pawn because you don't have knight f7, and all other squares are taken. So it's forced. Immediately, the evaluation, the first line shows a win for white. So when you force him to accept the sacrifice. Now, what's the idea? You make the queen. You must now check here. And I go here. I don't protect the queen, which is strange. Yeah. Here and here. And now you see the mating net. h4 is taken and the king takes the other square. He has a dark square bishop, so he's useless to check the king on f5. His knight on a6 is totally useless, so he has one knight to try to stop the mate. And what's the mate? I want to mate on d1. So you must stop it, and the only way to stop it is e2. Yeah. Bishop e4. Now I want to mate. What's the only way to stop it?
Knight.
Yes, even knight. The only way. Yes. Count how many pieces more you have. 3. But it doesn't matter. Yeah. So I go here. Now my idea: bishop c4 and e2. And okay, the dark square bishop is useless, and the knights are too far away. Yeah. So here, how you stop it?
Another knight.
Yes, c1 knight. So remember that Michael Tau calculated this line in his head and saw that everything works. Yeah. What you do now? Bishop b5 with the idea to mate from e8. Yeah. The only move to sacrifice. Check. Knight c7. The only way to stop it. And then bishop a4, and you cannot stop bishop d1 mate. And to see the last move, Tau said, of course, was the most difficult one because the move backward that you go. He saw all this line, yeah, and here you cannot stop the mate. That's it. You can sacrifice the knight on f3 and so on. But so it's amazing that the king is mated with one piece in an open board, yeah. And Tau saw it. So, and now the last story about Tau, because it's not so well known. Most of his jokes are well known. So, as you know, he smoked a lot and he drank a lot. And in 1979, he had to play a tournament in San Francisco, so on western coast. He had a flight to New York and then a connection, a domestic flight from New York to San Francisco. By that time in the United States, they prohibited smoking on planes. It's hard to believe it was a casual thing, but only in domestic flights in the United States. And they said to him that you cannot smoke on board when you fly from New York to San Francisco. And he said, but I cannot fly for 4 hours without smoking and so on. But they said, no, these are the rules. Now, what Tau did, he booked a flight from New York to Iceland, which is an international flight. It's like 4 hours or 3.5. And from Iceland, he took an international flight directly to San Francisco to avoid the American policy. No, this is a real story. It's absolutely crazy, yes, but Tau could do it, definitely. So thank you very much. This games and the game and the studies are in a link in the slides, and I would post it up on the website of the tournament. And any questions you can ask me after the lecture. So thank you very much, and good luck in the rest of the tournament.
If you go to
1 hour and 10.
If you go to the slide of the tree,
Slide 3.